Hello and welcome back to the last video for this chapter. In the last video, I talked about nucleophilic substitution reactions of haloarenes, and in this video, I will be starting off with electrophilic substitution reactions, which includes halogenation, nitration, sulfonation, and Friedel-Crafts reaction. You might have seen this in your class 11th. And at the last, I will be talking about reaction with metals, which includes Wurtz-Fittig reaction and Fittig reactions. So, electrophilic substitution reactions. Haloarenes undergo the usual electrophilic reactions of benzene ring such as halogenation, nitration, sulfonation, and Friedel-Crafts reactions. Halogen atom, besides being slightly deactivating in ortho-para direction, therefore further substitution occurs at ortho and para positions with respect to the halogen atom. The ortho-para dielectric influence of halogen atom can be easily understood if we consider the resonating structures of halobenzene as shown. So we have the image over here. So the lone pair from halogen gets inside and we get 1, 2, 3 resonating structures in 2, 3 and 4. You might have seen this already many times. So I'm moving forward. So due to resonance, the electron density increases more at ortho and para positions than at meta positions. Further, the halogen atom, because of its -I effect, has some tendency to withdraw electrons from the benzene ring. What is -I? Negative inductive effect, that is pulling up of electrons. In simple, otherwise withdrawing electrons. As a result, the ring gets somewhat deactivated as compared to benzene, and hence the electrophilic substitution reactions in haloarenes occur slowly and require more drastic conditions as compared to those in benzene. Now let us look at each reaction. For halogenation, the reagent is Cl2 in presence of anhydrous FeCl2, ferrous 2 chloride. So chlorobenzene, Cl2, anhydrous FeCl2, I get a substitution at para and ortho, and the major product is that of para-chlorobenzene. Next, nitration. The reagent is HNO3 in presence of concentrated H2SO4. So when I have chlorobenzene and make it react with HNO3 in presence of concentrated sulfuric acid, I get a nitro group at para position as the major product and ortho substitution as minor product. Similarly, in sulfonation, the reagent is concentrated sulfuric acid and little bit of heating is required, and in such a case we get a SO3H group at para position as major product and the ortho substitution is minor product as expected. Now the Friedel-Crafts reaction. The reagent can be RCl in presence of anhydrous aluminum trichloride or RCOCl in presence of anhydrous aluminum trichloride. Let's take the first reagent. Let's take chlorobenzene in presence of CH3Cl and anhydrous AlCl3. The product is a CH3 group at para position, that's the major product, and the minor product is the substitution at ortho position. Now if we take RCOCl instead of CH3Cl, we get COCH3 at para position. Instead of CH3, we get COCH3 at para position as major product and COCH3 substitution at ortho position as minor product. So these are the 4 electrophilic substitution reactions that haloarenes undergo. The first one is halogenation, second is nitration, then sulfonation, and within Friedel-Crafts reactions we have 2 reagents. One is RCl and RCOCl. Pretty simple, right? Now here is a question for you. Although chlorine is an electron withdrawing group, yet it is ortho-para-directing in electrophilic aromatic substitution reactions. Why? I repeat, chlorine is an electron withdrawing group, right? But still it is ortho-para-directing. Why? You can take 15 seconds, and if you want more time, you can pause the video. Okay, let's look at this solution. Chlorine withdraws electrons to inductive effect and releases electrons to resonance. I repeat, chlorine withdraws electrons to inductive effect and releases electrons to resonance. So it is a minus I group and plus R group. With inductive effect, chlorine destabilizes the intermediate carbocation formed during the electrophilic substitution. And with resonance, halogen tends to stabilize the carbocation and effect is more pronounced at ortho and para positions. We have seen the resonating structures. We noticed that the negative charge appeared at ortho, then para, then back to ortho, then went back, right? In the previous video also I showed you, and we saw it in the beginning also. So due to resonance, the halogen tends to stabilize the carbocation and the effect is more pronounced at ortho and para positions. The inductive effect is stronger than resonance and causes net electron withdrawal and thus causes net deactivation. The resonance effect tends to oppose the inductive effect for the attack of ortho and para positions and hence makes the deactivation less for ortho and para attack. Reactivity is thus controlled by the stronger inductive effect and orientation is controlled by resonance effect. By reactivity, I mean the deactivating nature, and orientation, I mean the ortho para directing nature of chlorine. Why is it? Chlorine is minus I plus R group. Because of minus I, electron is withdrawn by chlorine and this affects the reactivity. Due to plus R, electron is released by resonance and this affects the orientation. Hence, chlorine is ortho-para directing, but because of its electron withdrawing nature, it is deactivating. I hope this question is clear. Now let's move on to reaction with metals. And the first one we have is Fittig reaction. We have seen Wurtz reaction in the in previous videos, which involved reaction of haloalkanes in presence of dry ether and sodium to give an alkane, a coupling reaction, right? Coupling. So similarly, aryl halides also give analogous compounds when treated with sodium in dry ether, in which two aryl groups are joined together and is called Fittig reaction. So we take 2 moles of halobenzene, treat it with sodium in presence of dry ether, and I get a diphenyl plus 2 moles of NaX as byproduct. It is somewhat similar to Wurtz reaction, which I have seen in reaction of haloalkanes. Now there is something called Wurtz-Fittig reaction. Can you guess it? Yeah, some of you might have got it correct. Wurtz-Fittig reaction is basically a mixture of alkyl halide and a mixture of alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether, and it is called as Wurtz-Fittig reaction. It's basically a combination of Wurtz reaction and a combination of Fittig reaction. So halobenzene in presence of Rx, that is an haloalkane, with sodium and dry ether, I get a alkyl arene and NaX as byproduct. So with this we have completed this 10th chapter, haloalkanes and haloarenes in class 12 book, chemistry textbook for NCERT. And let me give you a summary of what we have learned. In the first video, I talked about classification, nomenclature, and the nature of CX bond. We saw that the carbon is partial positive charge and the halogen gets a partial negative charge. Then in the second video, we saw some methods to prepare these haloalkanes and haloarenes. The third video, I talked about physical properties and some polyhalogen compounds that are used in our day-to-day lives. The fourth video, we saw some reactions of haloalkanes, and in the next video, that is the fifth one, we saw stereochemical aspects of nucleophilic substitution reactions. In the previous video, I talked about nucleophilic substitution reaction of haloarenes, and in this video, we saw electrophilic substitution reactions of haloarene, which included halogenation, nitration, sulfonation, and Friedel-Crafts reaction. And the last we saw reaction with metals, which had Fittig reaction and Wurtz-Fittig reaction. I hope you found this lesson interesting and understood what was covered in these videos. Thank you for watching these videos. Goodbye.